Hello and welcome back to the channel. This is The Home Geologist, the series where we talk about and demo geologic principles using common household materials. Today we're in the kitchen again because there's tons of geologic principles that you can demonstrate with cooking, to the point where I was going to call this the Geology Kitchen until I learned there was already a series called that, and they actually make some pretty good videos, so you can go check them out. Today we're going to be talking about a subject near and dear to my heart. Impacts. Impacts are a ubiquitous geologic process. They occur throughout the solar system, in other solar systems. Things run into each other all over the place. And on Earth, unfortunately, a lot of impact craters get degraded and eroded because of weathering and our atmosphere, to the point where sometimes they can be difficult to identify. Fortunately, our nearest neighbor records over 4 billion years of impacts on its surface in relatively pristine condition. And I'm talking about the moon. On the moon, we actually have a record of meteorite impacts all the way from micro scale to, macro scale impact basin size craters, which are craters larger than 300 kilometers. Because impacts are so well studied, we do know a lot of their characteristics and how they form and evolve with different sizes and impact angles. Today we're going to be making simple craters, which are regularly round, bowl-shaped craters that form kind of on the smaller end of impacts. If you scale up from simple craters, you start getting into what's known as complex craters. And those craters can have things like central peaks, where the subsurface rebounds into a peak that solidifies. Larger craters often have rings of fault scarps that slump down back into the crater and modify the original rim. Now you can model impact craters yourself. If you've thrown a rock into some mud, then you've made a crater. It's basically that simple. What we're going to do here is create an analog for the lunar surface. In order to do that, we need two main components. We need a source of anorthosite, in this case a light colored material. Flour will do nicely. And we need our mare, or basalt, that covered the anorthosite on the near side primarily. And for that we'll use cocoa powder. We also have some chocolatey impactors to make our craters. What we have here is our anorthosite crust, which is the flotation portion of the differentiation of the moon 4.5 billion years ago. And I've also added a little bit of brown sugar for a different kind of lithology. And what we're going to do is bury that with some cocoa powder. This is our mare covering the anorthosite crust on the near side. So now we have our mare masking the underlying anorthosite crust. What happens next, you can imagine. A meteor comes into the gravitational orbit of the Earth and/or Moon and gets flung into the lunar atmosphere. And we get an impact. And what we're left with is an impact crater, sort of roundish, that exposes the underlying anorthosite lithology. And we can also see now that there's some white ejecta, which is the material that's flung out of the crater, that is now on the mare. And so you can use impacts as a sort of subsurface probe of the lithology of what's underneath the overlying material. That impact was more or less vertical. If we do a more oblique impact, then the ejecta gets flung more that way. It's on the counter over here now rather than over this way. We have our original impactor and then our oblique impactor, and you can see that crater is more elongated in that direction, where it's shallower over here and deeper over here. The chocolate chip is still buried in there. And so that's where you would find the impactor, if it survived the impact, would be sort of at the end of that oblong impact shape in the crater. There's another feature of impacts that we won't be able to model here, but there's a thing called shatter cones. And if you think of, say, tapping a hammer on a pane of glass and the cracks of that pane of glass radiate outward from the hammer, if you trace those cracks backwards, you can see where the point of impact was. It's a similar feature with impact shatter cones, where the force of the blast goes into the subsurface and creates a sort of cone of pressure that solidifies and hardens the subsurface, and then the point of that cone points back towards the direction of the impact. So that's one way you can tell if an impactor was oblique or vertical, depending on the orientation of the shatter cones. Now obviously this is a very simple model. We only have a couple of impacts here. What we have on the moon is actually 4 billion years of impact processes. There's actually this theory where about 4.1 or 4 billion years ago, there was actually an increase in the influx of impactors that kind of wiped out a lot of the history of impacts before that on the moon and in other planetary bodies. It's unfortunately difficult to do complex craters, but the effects of heat and pressure at those large scales almost liquefy the impactor and the thing that's being impacted into. It's difficult to see without slow motion, but perhaps the best way to model these complex craters is actually with some water. So if we swap this out, water does not belong in cookies, but we'll make an exception in this case. If we have our chocolatey impactor, there's a transient crater that forms, which then gets filled back in because it's so elastic and actually rebounds to the point where the central peak would form if that's solidified. Well, that's pretty much it for modeling impact craters in the kitchen. Really, we're just using this as an excuse to make cookies. So the next time you look up at the moon and you see white streaks around some of those large craters, you'll know that that's the ejecta from the subsurface that's been flung out away from those large craters. What we're going to demo today are simple craters, which are normally round craters with bowl-shaped bottoms. They're fairly simple to make.